The position of a rigid body is fixed by 3 coordinates for its center of mass plus 3 angles for its orientation. The most convenient set of angles is the Eulerian angles. Since only the angles between the axes matter, we let both frames share one origin. The plane carried by the body cuts the fixed horizontal plane along a straight line, the line of nodes. It is perpendicular to both the fixed vertical axis and the third axis of the body, and its positive direction is the cross product of those 2 unit vectors. The 3 Eulerian angles follow. The first is the angle between the vertical axis and the body's third axis. The second runs from the fixed first axis to the line of nodes. The third from the line of nodes to the body's first axis, each by the corkscrew rule. So any orientation is reached by 3 successive rotations. First about the vertical axis, which swings the line of nodes into place, then about the line of nodes, which tilts the body's axis down, and last about the body's own axis. Now write the angular velocity in these angles. It splits into 3 parts: the rate of the tilt along the line of nodes, the rate of the second angle along the fixed vertical axis, and the rate of the third along the body's own axis. These 3 axes are not perpendicular. Projecting each part onto the 3 body axes and adding them gives the components of the angular velocity. The first 2 each mix a tilt contribution with a precession contribution, while the third is the precession projected on the body axis plus the spin. If those axes are the principal axes of inertia, substituting into the rotational kinetic energy expresses it in Eulerian angles. For a symmetrical top, the result is especially compact, because the 2 axes perpendicular to the symmetry axis may be chosen freely. Using that freedom, put the body's first axis right on the line of nodes, so the third angle is 0. The components then become very simple: the rate of the tilt, the precession rate times the sine of the tilt, and the precession projected on the axis plus the spin. Use this to redo the free motion of a symmetrical top. Take the vertical axis along the conserved angular momentum and the body's first axis along the line of nodes. Since that axis is perpendicular to the momentum, its components are 0, m sinθ, m cosine theta. Comparing the 2 sets gives 3 results. The tilt never changes, so the angle between the body axis and the angular momentum is constant. The precession rate is m over the first principal moment, and the spin is m over the third times the cosine of that angle.